You're using neural networks right now. When you unlock your phone with your face, when an algorithm recommends your next video, when you type and a predictive model finishes your sentence, that's a neural network at work. But here's the thing. These systems don't understand anything the way you do. They don't think. They recognize patterns. So what exactly is a neural network? And why does it work? The name says it all, neural network. These systems are loosely inspired by how your brain works. In your brain, you have roughly 86 billion neurons. Each neuron is a small cell with branches called dendrites that receive signals from other neurons. When a neuron gets enough stimulation, it fires. It sends an electrical pulse down an axon to neighboring neurons. This is the fundamental mechanism. Receive signal, accumulate input, decide to fire or not, pass the signal forward. Now, artificial neural networks simplify this into mathematical operations. Instead of biological neurons, we have abstract units. We call them nodes, or neurons. Instead of electrical signals, we have numbers. An artificial neural network is organized in layers. Think of it like an assembly line. The input layer receives raw data. Maybe it's the pixels of an image or features of a medical scan. This is pure information, unprocessed. Hidden layers, and there can be many, do the actual work. Each node in a hidden layer takes input from the layer before it, performs a calculation, and passes a number to the next layer. What calculation? It's called a weighted sum. Imagine you're predicting whether someone should get a loan. Income matters, credit score matters, but income might matter more, so it gets a higher weight. The network multiplies each input by its weight, adds them all up, and then applies what's called an activation function, a mathematical gate that decides, does this signal matter? Is it strong enough to fire? Finally, the output layer produces the answer. Maybe it's a single number, the probability someone will pay back a loan. Or it could be multiple outputs. The network classifies an image as containing a cat, a dog, or neither. But here's what makes neural networks powerful. The weights aren't set by humans, they're learned. The magic of neural networks is learning. At first, all the weights are random. A fresh network is essentially guessing. You feed it an image and ask, is this a cat? It might say 87% cat when it's actually a dog. That's wrong. How do we fix it? We use an algorithm called backpropagation, invented in the 1980s. Here's the process. Step 1. Feed data through the network and get an output. Compare it to the correct answer. Measure the error. How wrong was the network? Step 2. Now work backwards. The algorithm asks, which weights contributed most to this error? It calculates how much each weight should change to reduce that error. Step 3. Adjust all the weights slightly in the right direction. Step 4. Repeat thousands or millions of times with different examples. Over time, the weights converge. The network gets better. This is learning. It's not learning like a human. It's not understanding concepts. It's pure numerical optimization. The network is fine-tuning its weights to minimize error on whatever task it's trained on. So why do neural networks work so well? The secret is compositionality. Early hidden layers learn simple patterns, edges, textures, colors. Middle layers combine those into more complex features, shapes, local patterns. Deep layers recognize high-level concepts, faces, objects, entire scenes. It's a hierarchy of abstraction built automatically through backpropagation. And because of the nonlinear activation functions, neural networks can learn curved, complex decision boundaries, not just straight lines. They can capture nuance. But there's a catch. Neural networks are black boxes. You can feed in data, get an output, and it works, but you often can't ask why. The weights don't have human-readable meanings. This matters for healthcare, justice, banking. Interpretability is still an open problem. Neural networks aren't magic. They're elegant mathematical systems that learn patterns from data through optimization. They've transformed what machines can do. They power computer vision, natural language processing, game-playing AI, drug discovery. But they're also not conscious. They don't understand meaning. They're pattern-matching engines, extraordinarily powerful ones. And that's why understanding them matters, not just as engineers, but as citizens navigating a world where these systems make decisions that affect real lives.